All right, our next speaker is Art DeGaetano from Cornell and the Northeast Regional Climate Hub, Climate Center. So Art, let me turn it over to you.
Thanks, Marty. And just to confirm, I'm running my own slides. Is that true?
You have control.
Awesome. Thank you. So, hello, everybody. Sorry I couldn't be with you all there in Washington today. I'm sure the weather's a little bit better than it is in cloudy and kind of snow flurry-y Ithaca today. But I guess we have to expect that for the beginning of December. So as the introduction said, I'm the director of NOAA's Northeast Regional Climate Center. So we're one of 6 centers across the country. So it seems like a pretty national group there. So each of you do have your own climate center that covers your region. And I know many of my colleagues interact with folks in the agricultural industry and with NEFA and things like that. We're mainly all at land grants in this case. So kind of just real quick, I've been kind of listening into the conversations, and I think really the themes that I'm going to hit on this morning really have hit on what people have talked about. Basically, what I'm going to do is do a quick overview of current climate conditions and relate that to some work we've done with indicators, basically broader agricultural indicators, but kind of touch on those that hit on insects. So clearly a lot of implications there, both from a temperature perspective affecting lifestyle and range, and I would argue management options. Precipitation does come into play in a number of cases, particularly from on the disease side of things, I should say precipitation and moisture. And then kind of this last area, which really is become kind of a buzzword or an area of active research within the climatological community, this idea of compound impacts. You might think of, I hit on wildfire there, but you might think of the impact of pests on wildfire, perhaps with increasing fuel loads and things like that in many of the forests out west. And then also environmental impacts, the kind of adaptation we might apply to manage some of the anticipated impacts of climate change, perhaps higher insect populations leading to more pesticide applications, which obviously ultimately have an environmental impact. So if I look at temperature trends across the U.S., this is from NOAA's Climate at a Glance. I've broken this up by season across the realm there, and pretty much kind of to give you the lay of the land, the long-term average is the black line that kind of runs horizontal across the screen, across the graph. And the blue line is just a simple linear regression for the data here. And again, I'm looking at seasonal average temperature. So really the take-home messages here is regardless of what season you're in across the US, we show a significant increase in average temperature. But it's this winter season where the increase is actually about 1/10 of a degree per decade greater. So over the last century, winter temperatures have increased by a degree Fahrenheit on average more than in any of the other seasons. And again, kind of looking at these graphs, fall might be a good example, or actually maybe I'll pick on the winter as well. The linear trend isn't all that bad in looking at that data. I'm sure some people may argue that the temperature trend has been fairly flat in through the 19 teens, through the early 1970s. But in all cases, we see an increase, particularly from the 70s onward. And we can attribute that to many things in the climate system, but that 1970 onward is clearly you need the increase in greenhouse gases to account for that. I think a striking figure here, sorry for the bit of the blurriness, but what I've done here is try to give you an idea of the spatial aspect of things. So what I'm doing here is in a gridded data set from NOAA, actually their new NCLIME grid data set. I'm looking at the long-term 1901 to 2000 average, And then to that, I'm comparing the averages in basically 30-year periods separated by 10 years. So what us climatologists like to use as the 30-year normal. And what you see is the long-term average was actually the early part of the century was much cooler than the long-term average in most areas of the country, except for the southeast. And as we move through, the early part of the 1900s was we see a lot more reds and pinks appearing, about a half a degree above the long-term average here in the 30s through the 60s. A bit of a cooling from the 40s and the 70s and the 50s and the 80s. Many might attribute that to the increase in aerosols in the atmosphere, reflecting some of the the shortwave radiation out of the climate system. But since we've cleaned up those aerosols in the intervening decades from the 60s onward, we see this dramatic increase in temperatures. And boy, I had to really look at this last one again, kind of was shocked to see how red it was. But clearly across the US, compared to the long-term average, we're averaging a good 1.5 degrees Fahrenheit above the long-term average, with an exception of the southeast, and that southeast again is still on the above normal side of things. We can do the same thing with rainfall. So I'm looking at seasonal rainfall here. And really, the picture isn't quite as dramatic in terms as far as the temperature goes. Same type of pattern here, the long-term average by the horizontal gray or black line and the linear trend by the blue line. So you can see in many seasons, particularly winter and summer, the trend and the long-term average aren't much different than each other, although there is a subtle increasing trend in seasonal rainfall here. And really where we see the bigger trends about a tenth of between a 500ths and almost a tenth of an inch per decade is in the spring and the fall in those kind of shoulder seasons. So in this case, we've seen about a 10% increase through the period of record. And again, we can see that in this same type of view on a spatial scale, comparing each successive 30-year normal to the long-term average. And you can definitely see the greenness appearing here at the end of the record compared to, I would say, the more droughty periods earlier on in the record. So definitely a moistening of rainfall, with perhaps the one exception being the southwestern parts of the United States and a little bit of the Intermountain West, where clearly droughts have gotten much of the press in recent years. So a lot of the examples that I'm going to give are out of this USDA report, which had a number of authors from across the country, where we set out to look at indicators for agriculture, or climate indicators for agriculture. And really here, kind of some of the earlier talks, kind of mentioned it, is really if we're to adapt to climate change or to monitor the effects of climate change, particularly in certain sectors, we have to be able to adequately look at how not just the temperature and the precipitation are changing, but how those temperature and precipitation changes manifest themselves on the types of systems that we're interested in. So I use an example here out of the report. How might this change in temperature affect an insect pest? So here, one of the things that we talk a lot about in the report is the number of generations of insects that we may see during a season. Here I am using an example from the Northeast. And if you're really interested in the example, it happens to be cabbage maggot, but that was really just used as an illustrative example. The development of the cabbage maggot is based on a base 40-degree Fahrenheit degree day. Here in New York, we typically see about 3 generations of cabbage maggot during the season. And you can see from the graph that that was indeed the case through most of this record, up through about the year 2000. But as we've gone into more recent years, perhaps the last 20 or so years of this record, we see a real shift in many places in this example across New York, seeing a fourth generation of this insect possible. And we can look at this across many parts of the country. Corn borer follows this quite well as well in the Midwest and in the southeastern United States. So the increase in degree days are really not only speeding up the development of insect pests, but also increasing the number of generations that one might see. The other one, again, out of this report, I'll admit this is not a pest-based example, but what it really does and why I've included it is it really kind of focuses on the phenology of things. So this could easily be an insect phenology as well as in our case here, apple bloom. So what I'm looking at here is, again, data. This is observed data on bloom dates, are actually a number of different levels of bloom date, from full bloom in the red to tight cluster to green tip in the green for apple. This is a New York example. And again, the thing to key on in here is I have dates along the vertical axis. So back around in the early 1980s, the full bloom date for apples was around May 15th. And as we've progressed forward, really this averages now around May 1st. So, actually here I'm doing the averages in the first part of the record and the last part of the record as the dotted lines. And, over the last 40 or so years, we've seen this increase by about a week in whether we're looking at full bloom or tight cluster or green tip. So the phenology of these phases are appearing about a week earlier each year. Also look at a metric, an indicator that might be indicative of some of the ranges of pests. So here I'm looking at the lowest winter temperature. So this is not the average minimum temperature, but the coldest minimum temperature that it might get. I'm looking at a case in the upper Midwest. And what we've seen is this value, again, increasing through time. So this has implications for the survival of some insect species that might be, might expect to occur quite frequently to the south of a location than the upper Midwest. But here, this warming has allowed a more overwintering potential for different insects, pests. And with these minimum temperatures, I think this is a striking graph because, again, it's the same type of figure that I've used before, where the long-term average is this dark black line. And clearly, as we move from the 70s onward, the majority of these dots are above what used to be considered the long-term average. So you almost see a sharp transition where the majority of these are below the long-term average through about the mid-1960s, and then they jump above from the 60s onward. Another example that goes more to the environmental type impacts of these, I'm looking at the application of pesticides. This is data from Ziska, one of the authors of the report, one of my colleagues. And they were looking at genetic fungicide and insecticide application on soybean. And really what this example of an indicator does is kind of substitutes space for time. So really here, this change, this warming of minimum temperatures here across the gamut here is more of looking at different locations through time and comparing them to the number or the amount of active ingredient of fungicide or insecticide. Really what was made in the report is the fact that as we move to higher minimum temperatures, again, consistent with the warmer winters that I showed on the last slide, and also the warmer winters that are projected under climate change, one might imply the need to increase the application of both insecticides and fungicides. Again, not only due to perhaps the increase in generations of insects or added increased insect pressure, but also due to the efficacy of these chemicals. Right. So I'd like to kind of shift gears here and go from looking at the past to what might be going on in the future. And before I do that, I'd like to do a little bit of climate change 101. And basically, here, kind of a complicated slide, but I wanted to point out two things by this slide. Really understanding what's going to happen in the future really boils down to us in terms of how our CO2 emissions pathways evolve. And there are a number of ways that this is done. Many of you that might be familiar with past climate assessments, these representative concentration pathways, RPC 8.5 and so on, might be what you're familiar with in terms of scenarios. In the latest kind of runs of the newest generation of climate models, the CMIP6 models, they've also used a bit different scenarios development pathway there. So they're basically added kind of more subtleties to these. The point that I want to make is there's one that's analogous to the old RCP 8.5 up here, but there are several that are more middle of the road. And in these models, really these middle of the road scenarios are really what people have been keying in on as maybe the more likely scenario of society's socioeconomic pathway. So again, really, this is the gigatons of CO2 that might be emitted in each year, the black line being the observed emission. And really here, we're kind of at a cusp here where if I had given this talk probably a year or two ago, I would say we're on this RCP 8.5 type scenario, this very high emissions scenario. But now, really, the kind of thinking is more of this high path given by the yellow line. So that's kind of perhaps a positive in the new generation of climate models that society has, we kind of see this plateauing of CO2 emissions in any of at least of the commitments that are in play. We're likely to follow these lines. The lower emission scenarios really become kind of pie in the sky, particularly in this case, because I think added commitments to bringing CO2 down are fairly minimal. And to achieve some of these high-end goals, we'll actually have to actively remove carbon dioxide from the atmosphere. Again, any of these future projections are based on climate models, a big complex set of calculus problems. There are many climate models in play across the globe, probably about 30 or 40 from different modeling groups. The point that I want to make here is all of them work on some type of a grid system. All of them bring in multiple aspects of the climate system. It's not just the atmosphere, it's the oceans, the land surface, the hydrology, the clouds, pretty much as the chemistry in the atmosphere. As time goes on, these models get more and more complex in terms of the number of systems that they bring into play. Really at the heart of all 30 or 40 of these models are the same base physics. The physics of climate change don't change, but what varies between the models are what are known as parameterization. It's how the different modeling groups handle aspects of the climate system that in which either the physics or the science aren't 100% known. So there's assumptions that come into play, or things that operate on a scale that's smaller than the grids of the climate model. Most modern climate models today work on a grid system that's about 100 kilometers square. That's quite a bit better than, even 5 or 10 years ago, where we were basically talking about 200 kilometer resolution. But several key aspects of the climate system, most notably clouds and what makes clouds reflective and such, really operate on spatial scales that are much, much smaller than the grids of the climate model. And these are the things that the groups need to parameterize. What's also done to these models is, particularly for impact assessment, is they need to be downscaled. to go from that 100-kilometer resolution to, as low as 4 or 5 kilometers in resolution. This is typically done statistically. It can be done dynamically with higher resolution models. But basically, the point is that this downscaling methodology really adds, what it does is it does several things. It accounts for the biases that are in the GCM. So it's a way of taking these models that really don't know anything about the observations and adjusting for the biases in the models to kind of get them to at least match the observations in the historical period. And then that bias correction is assumed to persist into the future. It adds spatial detail, localized information that might not be present in climate models. The Great Lakes are a good example of that. Key elevation features, coastal features, all of that kind of fall into that second bullet there. And really what we want them to do is not really to distort the global model's climate change signal. So a bad downscaling method would say something very different on how the climate model or the climate evolves through time. So if we look at this, this compares the models to observations, offers observations in black, the two generations of climate model in the gray and the blue being the most recent, and the shaded area kind of showing that uncertainty among the different models. So particularly since the 60s, the models have done a good job of tracking the observations. The two generations of climate models really say about the same thing in the historical period of time. And for this, looking at global average temperature, there is substantial variation among the models. Some are showing a warming through the presence of about 0.7 degrees centigrade. I'm switching units here again. And some showing warming about double that. So there is consistent variation or a considerable variation among the models. But again, most honing in on this kind of median value here of about 1.5 degrees of warming over the last century plus. Where things get complicated if we go to look at the impacts is really has to do with this variation of between the models and also their ability to estimate or predict or project other components of the climate system. So again, kind of a complex graph here, but really the idea is we want to be in this upper right quadrant. And here it's where we understand the causes or how climate change or how increased greenhouse gases affect the climate, and also knowing where we have the data and we can see how this is playing out. So things like rainfall and temperature and cold waves all fit in there very nicely. But if we start to talk about things like snowfall or extreme weather or windiness or even droughts, the complexity of these systems adds more uncertainty to knowing how these will play out in a changed climate. We have some information about that, but not quite the specificity. So looking at some examples, again, shamelessly plugging some Cornell websites here. This is the URL there is our climate change in a county website. What I'm showing here are data from the newest generation of climate models. I'm looking at base 50-degree days as an example. The dots represent observed conditions, so measured with thermometers. The green line is the average of about 30 climate models under a high emissions scenario. So we're seeing how those represent the past climate conditions and the projections into the future. And the shading as before kind of shows the range among the different climate models, so the warmest to the coldest climate model. So some points to make out under this case is the models do a fairly good job of replicating the observed data. All of the data basically fall within the envelope of the model in these years. and the average of the models do a good job of replicating the average of the observations. The trends since the 70s or 80s are replicated by both the models and the observations. And then we can see how that extends to the future. So in this case, sort of in Cornell's backyard, we're typically just above about 2,000 degree days in a season. By the end of the century, that degree day accumulation is projected to double in that case. And again, you can kind of see reaching about 3,000 in about 20 years in this case. Kind of even this season, we actually approached that 3,000 mark in a fairly warm extended season. If I shift ahead and look at a lower emission scenario and kind of play with this a little bit, and if I don't get you too sick toggling back and forth, really the thing to note is the end of the record is really what is affected. Then the next few decades really show little change in this lower emission scenario, but it's what's going on at the end of the century. Kind of the impetus that's built into the climate system is really reflected there. Kind of shows our kind of society's role in reducing some of the impacts that we might see. Kind of looking at a couple of different variables here. This is again very cold winter temperatures, days with a minimum below minus 20 degrees Fahrenheit. These are the counts of number of days kind of across the state of Michigan. And so what we see a fairly common occurrence even now in the recent part of the record, somewhere between 6 to 10 of these events. But as we move on through time, that becomes almost non-existent from the mid-20s onward. Picked minus 20 because that's tends to be a threshold for something like hemlock woolly adelgid to survive the winter season. So a forest pest here in New York's Adirondacks and across the upper Midwest. That timing of bud break comes back again. So the same view I showed here in terms of phenology earlier, but now going out until the end of the century. So here's that observed kind of May 15th, May 7th, full bloom date for apples. And as we move on through the end of the century, almost 2 weeks earlier yet again in this case. So a real progression of this timing of life cycles of pests and in some cases diseases, in this case the phenology of things. Ranges. So again, going back to something out of the indicators report, the top graph shows the current areas that basically show the range of suitable for cattle tick. Sorry, I'm forgetting the name of the species that's involved here. You can see really in the present climate, really confined to the Mexico-Texas border here in red and southern parts of Arizona. As we go out to mid-century, see a lot more color on this map, indicating an increase in the areas that are suitable for cattle tick. And the way this graph works is the colors represent the number of different climate models that show a suitable habitat. So in this case, it's not only showing the suitability, but it's sort of giving you an idea, at least in my mind, of the uncertainty that the climate models paint. So clearly by 2050, that suitable area expands across very much all of the state of Texas. You might argue that actually that same area in Arizona is there, but actually becomes sort of less suitable in some cases because there's an upper and lower bound for this insect. The California Central Valley really pops up, and an expansion across a good part of the Gulf Coast in the majority of climate models in this range. Up into Oklahoma and Arkansas, only the warmest of the models are showing that as a range expansion. And again, kind of looking at that range expansion for any number of other things. What I'm looking at here are basically the number of degree days that are accumulated across a growing season, and the kind of the should have I don't have color bars here, but the darkest of the blues are 2,000 degree days, and the warmest of the reds are 5,000 degree days, base 50. And so basically, back in the 61 to 90 period of time, a good part of the upper Midwest failed to see or just barely achieved 2,000 growing degree days. If I look across maybe a place like Illinois, a sharp gradient from on the order of 4,000 to about 3,000 degree days across the state, and the 5,000s being confined to pretty much the Gulf Coast. As we move through time, and basically, look at maybe something that looks more like the current climate, you can see that expanding. You can see the dark blue, the less than 2,000s decreasing. And by the time we get out to mid or late century, really no gradient across the state of Minnesota. Everybody's seeing at least 5,000 degree days in a season. The 2000s pretty much totally devoid in all areas, and actually even the 2500s, kind of more in almost somewhere between 2,500 and 3,000 now across the Midwest. So very, very much implications here for what we might see moving forward through the centuries. And as I kind of start to wrap up here, I want to say one point here is, one of the new areas or one of the things that we're looking at climate science really has to do with not only changes in the magnitude of temperature and precipitation, but really how persistent weather is, how persistent we get locked in different patterns. And this has profound implications for things like drought, things like rainy periods and such. For those of you in the Northeast, right, we've endured a very dry period up until this change in pattern that came over the Thanksgiving weekend. A very dry September, a very dry October, a very dry early November. And a lot of this relates to this idea of weather persistence, that weather systems don't really move as quickly as they have in the past. The underlying cause of this is under climate change, the Arctic warms quicker than the mid latitudes. And what that tends to do is decrease the strength of the jet stream. And when you decrease the jet stream strength, weather systems don't move as quickly from west to east. In addition to that, the pattern of the jet stream tends to be more meandery. It has more bumps and wiggles in it. And those bumps and wiggles kind of tend to close off and kind of separate themselves from the flow, which results in not only these persistent weather patterns, but an enhancement of extremes, both on the hot side and on the cooler side. So when we have these cold snaps in the winter, it is related to this weakening of the jet stream and allowing a relaxation of more stronger troughs and ridges. And then as I kind of close off, kind of a plug and maybe a call for persistence. The work we're doing right here in my shop right now, we're actually looking to make this indicators report that we've worked on kind of living. So to kind of take many of the things that we looked at in terms of indicators and providing snapshots that change from year to year and such. So what I'm showing here again, this is a work in progress. Kind of start off on this site with what I would call a national view that kind of shows departures from normal. So this is data from this past growing season. And basically it's showing the areas in the yellows and the oranges as areas that have seen more on the order of 10 to 30% more degree days during this past season. The green areas are slightly above, but notice no blue. Nobody has seen less. And then if I drop a pin on a particular location, it basically goes off to our database and basically gives some data which hopefully are usable in an ongoing type decision-making process. So for this location where I've dropped a pin in Nebraska, it's showing the accumulation of degree days through this current season. So again, just kind of looking at the historical data. If I was giving this talk in July, the graph would stop here, obviously. So this goes right through present. It gives a long-term perspective of kind of where we are. So how does what we see this season compare to what might have been seen in the past? So this idea, again, at this location early on, many cases below the long-term average, and here many cases above. The blue dot is the highest on record. And then kind of getting into management more, might be able to set some thresholds. So I've set a threshold here. I guess I don't have that being displayed there, but a threshold of, let's say, 2,000 or 3,000 degree days for, I guess it is 2,000 as my threshold for perhaps a certain corn phase or an insect phase. And I can see how that has changed through time. So the idea here would be an earlier occurrence in this case. So really what we're looking at in this call for assistance is really clear indicators that have a clear management application to them. So with that, I think I've used up my time, and I guess we go to questions.
Yeah, Allison? Yeah, I have a question. So you had that slide where you could capture the difficulties of capturing like precipitation or hail or any of those. One thing that I noticed that you didn't have listed there was humidity. And as a plant pathologist, that's certainly something that I'm always interested in. And I'm wondering if that's something you do look into. And then I have another follow-up question after that.
Yeah, I wanted to share my screen here. Let me get that back. Sorry about that. So as I bring that up, yeah, humidity's on there, and I would say humidity is in one of those areas of the graph that you really don't want to be in. It's not. I guess we want to go there basically. Let me bring that up. So, yeah, I would say one of the aspects with humidity is why I'm not says I'm sharing, but I don't see my slides. So. One of the aspects with humidity is really, what do you mean by humidity? You know, the climate models are good at looking at things like specific humidity, grams of vapor per grams of dry air or something like that. And I contrast that to something like dew point or something like relative humidity in those regards. So really the climate models have that moisture component to that. They have that as at the large GCM scale. There haven't been many efforts, or can't even think of any efforts that have attempted to downscale that to, say, a field level or even a 4 or 5 kilometer level. So that's something that is that's something that's lacking. I'll leave it at that. And fairly, where would I put it on that graph? Actually, our understanding of how moisture in the atmosphere goes up with climate change is actually quite good. You know, as we warm the atmosphere, warm the oceans, there is going to be more vapor in the atmosphere. But when you look at something like relative humidity, the other thing that happens is the atmosphere is able to hold more moisture. So even though we're adding more moisture, that ability to hold more moisture kind of works against you in terms of relative humidity. And any work that I've seen done on that, actually relative humidity stays fairly constant through time or actually decreases a little bit. So that was a long-winded answer. Sorry for that.
No, that was great. Thank you. My other question was more of actually just a comment. So you had a couple of slides that were showing like the bud break of apples on apple trees. And one thing that we've experienced in Maine is that we get these warm summers, warm falls, and then a quick reduction in temperature so that our apple trees are not fully going into dormancy. And you can see half the tree went through dormancy and the other half didn't, which is reducing the yield by about 50% and then adding stress onto it. So I don't know if that's something that you've looked into, but it's certainly something that's an issue in Maine.
Yeah, actually, we've looked into that a lot and kind of deviated from that, from not thinking that as a pest perspective for this. But actually, a unique situation there where we have these warmer winter temperatures that really, really speeds up the development. The, the the blossoms start to advance, as kind of I showed in my graphs. But even there, that cold snap that might come after there is really the thing that's really predisposing. Things like apples, things like peaches, particularly in New England, in New York, and Michigan, to these untimely freeze events that we've seen many times again over the last couple of years. So it's really the idea that the increase in degree days and the earlier, the earlier development in the winter, up in the Northeast, they meet their chill requirements, so they're really primed to bloom very, very early, given warm temperatures. But we have these cold snaps. Really, what we see is that, especially across the northern tier of the U.S., it's not as much the change in temperature that increases the risk of frost, but it's subtle changes in the variance of temperature, the standard deviation. We don't see much of that with climate change, but in the current climate, as we're kind of in that transition, as we still get cold enough and we're kind of moving in that direction, these swings in temperature are really the thing that are driving the frost risk in things like apples and peaches and stone fruit.
A couple of questions online. First of all, Caroline asks, can you share what might be a drought metric that would capture the changes we're seeing in the Northeast with these stalled weather systems?
Yeah, I think any drought metric, it really works well. Something like, we use something that's called the Standard Precipitation Index. It's really, it's an index based on how different precipitation is to a longer term kind of what we would call normal. And I hesitate to use normal there because obviously the normals are changing. There's also a metric that brings in evaporation, which we didn't talk about. So the idea here with this persistence is really in most areas of the country, and I'm kind of neglecting the West and the Southwest, but kind of bringing my Northeast, even Midwest kind of perspective there. What we expect to see in terms of these more persistent weather patterns is shorter term droughts, more frequent shorter term droughts, something that might last a month or 2 months, along those lines in a temporal scale, as opposed to, a multi-decadal drought, something like the 60s drought here in the Northeast, or the longer term droughts that areas in the West have experienced. So really anything that brings in precipitation, you can see that in streamflow metrics and things like that. Really something that characterizes that short-term aspect of drought. Actually, soil moisture is a good metric for bringing in as a drought metric for some of these stalled weather systems. A lot of the new soil moisture-based drought metrics also include evapotranspiration as part of their calculation.
Len, Len Coop, you've got a question online?
Yeah, first, I just want to address the idea that maybe the weakening jet stream is allowing more spillover of Arctic air and causing frost at odd times and upsetting cold hardiness and killing trees later in the spring from frost damage. And then my question, and you could address that comment, but my question is, I didn't quite understand the reasons behind the RCP assumed to be dropping from 8.5 to 6. What's behind that kind of optimism?
Yeah, I guess that's not climate optimism. I guess that's more the socioeconomic optimism. But basically, that broader community of both climate modelers and socioeconomic people that look at that. Again, these determinations were made a year ago, so I wouldn't say if that optimism may have been false or not in the coming years. But basically, looking at trends in greenhouse gas emissions globally, those have been going down through time, and looking at projections for commitments and things along those lines. And also the fact that there has been a plateauing. It's subtle in that case, but we're clearly not on that upper pathway. We'll see how that plays out in the next few years.
Art, when you say the emissions are going down, are you actually saying that the rate of increase is slower, or that the emissions themselves are decreasing?
The rate of increase is decreasing, if that's what you're asking. We're right. The emissions themselves are not going down, but the rate of increase is not as high.
That's
The rate of emissions is leveling off.
All right, thanks, Art. We're going to go ahead and move on to our next speaker.